So now we're getting into the 5 factors of soil formation. We talked about weathering, right? That's where our parent material breaks down and starts to form the young soil. Now, once a young layer of soil forms, the process doesn't stop. It continues to age and develop over thousands of years. Soil scientists have identified 5 key factors that operate during this ongoing process of soil generation and development. These are parent material, climate, life or organisms, topography or relief, and time. So the handy acronym that I mentioned when talking about the learning objectives, this CLORP, or I say CLOR-PT, is a way that the scientist Hans Jenny discussed it in his reports, where it's the CL is climate, O is organisms, R is relief, P is parent material, and T is time. So you can say that over time, climate and living things act on parent material with a certain topography to create soil. However, there's another factor to consider. Some have even suggested that human activity should be considered a 6th factor, as we've modified most soils to some degree. We'll discuss this concept in more detail later in this lecture. Now, we're going to stray from the order described by the acronym CLOR-PT and following the textbook order and start with parent material. All right, first up, parent material. This is the original source of most soils, the solid, unweathered material of the Earth's crust. When this rock breaks down into smaller particles, it becomes the parent material for soil, also supplying essential plant nutrients. The type of parent material heavily influences the initial mineral content and texture of the soil. For instance, soil from sandstone would be very sandy, while soil from limestone might be rich in calcium. It could be bedrock that weathers in place, or it could be materials moved by various forces. We categorize these soils based on where their parent material originated. Residual soils are formed directly in place from the breakdown of bedrock. Think of soil forming directly on top of the rock it came from. These soils tend to form very slowly because the solid rock has to weather first. And secondly, you have your transported soils, which are much more common. These develop from weathered material that has been carried from somewhere else by agents like wind, water, ice, or gravity. Because the material already weathered, these soils generally develop more quickly. So what kind of rocks are we talking about as parent material? Well, geologists classify rocks into 3 main types. You have igneous rock, sedimentary rock, and metamorphic. Igneous rock, it's the basic material of the Earth's crust, formed by the cooling and solidification of molten material from deep within the Earth. Examples include, which are the most common, granite and basalt. Granite's hard, coarse-grained rock, weathers slowly, and it creates acidic, sandy soils. Basalt, it's softer, fine-grained, weathers to less acidic. Igneous rocks are also very rich in essential plant nutrients. Sedimentary rocks, these form when loose materials like mud or sand is deposited by wind, water, or other agents, and then slowly cemented by chemicals together. Examples are like sandstone, limestone, shale. Okay, and limestone tends to be high in calcium and weathers into higher pH soils. Shale, sandstone, typically more acidic. Metamorphic rocks, these are some type of rock, igneous, sedimentary, or even a different metamorphic rock. And it gets squeezed and heated for a long time, causes that rock to change. Such as like limestone becomes marble, sandstone turns into quartzite, and these tend to be harder than their parent rock, making them slower to weather. Gneiss is a cool one. That's this right here. This is metamorpho granite. I'll show you these in the lab as well. It's got this cool banding. As we talk geology a little bit, it's important for you to have a basic understanding of the rock cycle. We'll discuss this in class, this diagram, and go through it a little bit more. But for right now, you take a look at this, you got your three types of rocks. You have these processes which that material cycles through and can change from one rock type to another. And our soil is sediment that is less than 2 millimeters in diameter. Everything else above that's not counted as soil, but that's the relationship that soil has with our parent material. Again, we'll talk about this more in the lab. But let's talk about how parent materials gets transported. These are transport agents of parent material. First, let's look at glacial ice. Now, over the past 2 billion years, massive glaciers have covered much of northern North America. As they expanded, they crushed, ground, picked up, and transported vast amounts of clay, sand, and rocks, and depositing them as glacial drift. This drift includes material called glacial till, which is material simply dropped in place as that ice melted. Often it's variable sized and dense. Then you have glacial outwash, which is coarser, sandy, and gravelly materials washed away by the meltwater. Then you have lacustrine deposits. This is where finer particles that were in that runoff then get settled into ancient glacial lakes. Okay, so that's ice. Another agent of transport would be wind or aeolian deposits. Wind can carry the parent materials, forming sand dunes. They got sand dunes in Nebraska. But it's very important wind deposit material is called loess. Okay, loess. And they're really great for agriculture. They're very fertile. And, you got a lot of that in Iowa and Illinois. This image here relates to glaciers of North America. This is kind of the most southern the glaciers made it. So moving on to other transport agents, whenever soils whose parent materials were carried and deposited by moving fresh water, we call those alluvial soils. And this diagram from your textbook, it's talking about several features on the Earth's surface created by moving water and depositing sediment. such as floodplains. Okay, you know what a floodplain is. Typically fine particles, excellent for agriculture, very nutrient rich. As a stream would kind of erode down through uh, deeper, those old floodplains get kind of left behind and new ones are made. That's what river terraces are called. Alluvial fans, that's where, just coming out of the mountains where things will pile up. The opposite of that, kind of in the ocean, you would have deltas. Okay. Um, Very fine grain sediment. Let's see what else we want to point out. Talk about lacustrine deposits like glacial lakes. We'll look at a river model in lab and kind of look at these features some more. But key is alluvial, meaning water transported. Floodplains are very important to ag and nutrients. So to wrap this up, this section here, the other transport agents would be gravity, which we use the term colluvium. You've probably heard talus slope, okay? Pile up of material. As this rock crumbles, it falls. This also kind of resembles what a alluvial fan would be. If water would be rushing out of here, it'd pile up material. Volcanic ash. So a volcano blows, it's going to deposit material all over the place. That's transport of broken up rock fragments. And then we also got to look at organic deposits. Now, the organic deposits, most soils are considered mineral soils, which means they have less than 20% organic matter. But organic soils contain 20% or more organic matter. So 20% is kind of that cutoff. These form underwater usually when aquatic plants die and like low oxygen conditions preventing decay, causing the remains to pile up and eventually filling in lakes to create these rich organic soils. So what we'll do in class is we'll take all of those agents of change or agents of transport and we'll kind of map out, diagram if you will, all those terms and some characteristics that kind of put all of that together and review those terms. Again, vocabulary, we're learning the language of soil science, so learning those terms will be important. But now that we understand aspects of parent material, let's see how it plays out across the United States. This map's a fantastic visual representation of the major parent materials that have given rise to the diverse soils across the U.S. Each color represents a different origin story for the soil, whether it's formed from ancient rock, wind-blown dust, glacial deposits, or river sediments. You can see how dramatically it changes from one region to another, explaining why soils in Iowa are so different from soils in Arizona, for example. Now, let's focus on our home state here of Maryland. Maryland's a particularly interesting state when it comes to parent materials because it has a really diverse geology, reflecting its position across different physiographic provinces. This diversity in parent material is the primary reason why we have such a wide variety of soils right here in our relatively small state. As you learned in dendrology, let's think about Maryland's major regions. First, let's group the Appalachian Plateau and the Valley and Ridge in western Maryland here. Here you'll find soils formed from shales, sandstones, and limestones, leading to very different soil properties depending on the specific bedrock. Soils from shale can be heavy and clayey, while those from sandstone will be very sandy. Next, the Piedmont region over here. Much of the soil here comes from the weathering of metamorphic rocks like schist, gneiss, and granite. Granite, not a metamorphic rock, it's a igneous rock and becomes gneiss after it gets heated and squeezed. These parent materials will often break down into a mix of sand, silt, and clay, creating, kind of rolling hills and really good agricultural lands. And then we'll take a look at the coastal plain here. It's dramatically a different story compared to the rest of Maryland. Here the soils are predominantly formed from unconsolidated sediments. All this erosion from this stuff getting deposited down here. And, meaning loose sand, silts, and clays that were deposited by ancient seas and rivers as the coastline changed over millions of years. These soils tend to be sandy, often with distinct layers from their depositional history. So as you can see, even within a single state like Maryland, the underlying geology, the parent material, gives each region its unique starting point for soil development. This initial recipe ingredient will heavily influence the texture, mineral content, and even the natural fertility of the soil, setting the stage for how climate, organisms, topography, and time will further shape it in a complex and vital living system we rely on. Before moving on to our next factor, let's review a little bit with some questions.